As embryonic development continues, the conceptus travels through the uterine tube towards the uterus. By day 4 or 5, it becomes a blastocyst. This is a fluid-filled sphere. At this point, it floats freely in the uterine cavity, nourished by uterine secretions until implantation begins. This transition will mark a critical stage in early pregnancy and is the basis for blastocyst stage IVF embryo transfers. Here are some review questions to help you understand the content in this video. So let's take a moment to consolidate. Can you define a zygote, morula, blastocyst? Could you even draw them out? What cells of the blastocyst become the embryo, and what contribute to the placenta? Think back to the earlier discussion on epigenetic reprogramming. When is DNA methylation at its lowest and why? And what is asymmetric cell division? Why is it needed for proper development? During week 1 of development, it includes fertilization, cleavage, and then the formation of a morula and a blastocyst. So we can see we start with our oocyte here. In the uterine tube, we can see this is the point where we've undergone fertilization. The sperm met the egg, so we have a fertilized egg, which is a zygote. We then see as we travel down the uterine tube, we are going to have replication, or division, I should say, and that's going to lead to our 4-cell stage after about 2 days post-fertilization. We then get to a morula, which is a solid ball of cells, around 3 days, and then we have an early blastocyst from the morula hollowing out and filling with fluid. That's kind of our blastocyst cavity. This is around day 4. And then around day 6 to 7, we will see implantation of the blastocyst. And the blastocyst now has a sphere of trophoblastic cells and an eccentric cell cluster called the embryoblast. And this is around 1 week. So this is in this 1 week time. These early mitotic divisions that are occurring do not increase the overall size of the embryo, but they create smaller cells with a higher surface to volume ratio. This will facilitate nutrient uptake and waste elimination, which is necessary for survival of the conceptus prior to implantation. Cleavage is the series of rapid mitotic divisions the zygote undergoes as it travels towards the uterus. These divisions yield to smaller and smaller cells, as we saw before, which are called blastomeres. Then they don't have increasing total volume. By around 72 hours post-fertilization, the embryo is a morula, which is a solid ball of 16 or even more cells. This process will set up the stage for cavity formation and differentiation into embryonic and extra-embryonic lineages. The blastocyst will have 2 distinct cell populations. The trophoblast, which we can see here, which are a layer of flattened cells that will form part of the placenta, and the embryoblast, seen here, or inner cell mass, which will become the embryo proper, or the developing fetus eventually. The organization here is crucial because cell fate is now being determined, and the first signs of specialization or differentiation are emerging. Around day 4 to 5, the blastocyst will reach the uterus, so the embryo is now referred to as a blastocyst. The trophoblast cells will begin to secrete immunosuppressive factors to try to evade maternal immune detection, because we don't want this identified as not self and destroyed. These same cells will also help to form the placenta. So trophoblast has kind of these 2 major functions. The interplay between embryonic and maternal tissues will underscore the complexity or even fragility of early pregnancy. Implantation begins on day 6 or 7 after ovulation. We often say that our blastocyst sticks on day 6. So that's implantation essentially. The blastocyst will adhere to the endometrium, that is the process of implantation, and then it will begin to burrow inward. The trophoblast, that layer of cells that are flattened, will secrete enzymes that digest the uterine lining and will allow it to embed within the uterine lining. Meanwhile, the inner cell mass, the embryoblast, will form into two layers, the epiblast and the hypoblast. Together, these will make up the embryonic disc, which is the foundation of the future embryo. So during this implantation time, the blastocyst will float in the uterus, nourished by secretions. Once implantation starts, the trophoblast cells will bind to the endometrium at receptive sites. An inflammatory-like response is triggered using these enzymes, which will increase vascular permeability. Immune cells are recruited, and the uterine lining prepares to support the developing conceptus. However, about 2/3 of blastocysts fail to implant, many due to a chromosomal abnormality. And we can see this process here. We're seeing this blastocyst adhering to the uterine wall. We're seeing the trophoblast invading the uterine wall, and we're seeing the implantation continuing where the embryoblast has pretty much become a bilateral disc or a bilayered disc, and we've almost fully gotten within the uterine wall at this stage. As the trophoblast proliferates, it will form two layers. And I don't know if I have this listed here. Let me see if I do. I do. The cytotrophoblast is the cellular inner layer, while the syncytiotrophoblast is a multinucleated mass that invades the endometrium. The syncytiotrophoblast will secrete enzymes that digest maternal tissue, enabling deeper implantation and access to maternal blood flow. This structure will become the primary source of HCG moving forward. So cytotrophoblast, here, cellular inner layer. Syncytiotrophoblast is going to be this outermost layer. As the embryo embeds itself, blood will leak into the space, and the endometrial tissue will eventually grow around the blastocyst, sealing it in. Implantation is typically complete by 12 days post-ovulation, just as menstruation would typically occur. The corpus luteum is maintained by HCG, preventing menstruation and supporting progesterone production. This is the first endocrine function of the embryo. Early on in implantation, two important cavities will form. The amniotic cavity is enclosed by epiblast cells and will eventually surround and protect the embryo. The yolk sac cavity, which is formed by hypoblast cells, will provide early nutrition and plays a role in blood formation. By day 11, once the blastocyst is completely implanted and enveloped by endometrial tissue, this is a critical milestone in gestation and really kind of moves us from this early onset stage to further developmental processes. As the endometrium is continuously eroded, and as the blastocyst burrows into the lining, it becomes surrounded by a pool of leaked blood, and the surrounding endometrium will start to form a seal, and maternal blood will begin to pool near the trophoblast. This blood supply is really crucial for early nutrient and gas exchange, and again, by day 12, the implantation is secure, and the embryo begins to signal its presence biochemically, primarily through HCG secretion. The hormone human chorionic gonadotropin, or HCG, is secreted by trophoblast cells and later by the chorion, and it maintains the corpus luteum, which continues to secrete progesterone and estrogen, thereby sustaining the endometrium. HCG levels will rise through the first trimester and then decline as the placenta takes over hormone production. Clinically, this is the test that we use, the hormone that we use to detect pregnancy using a pregnancy test. We can see kind of this timeline here in this graph based off of weeks of gestation. So here's a conceptual prompt. By week 2 of development, it's often called the week of twos. Explain what this means by terms of cell layers of the embryonic disc, membranes, and cavities. Well, we think about the two germ layers of the embryonic disc. the epiblast and the hypoblast. The two cavities, the amniotic and the yolk sac, and the two layers or two membranes of the trophoblast. These twinned structures reflect the embryo's increased complexity and increased organization.